Hello, welcome you all in organic photochemistry. Today I will explain Jablonski diagram in which I will tell how the excited molecule can undergo relaxation by various process. In my previous lecture, I gave you the introduction of photochemistry and I explained various laws which governs the photochemistry like Grother-Straper law, Stark-Einstein law, Beer-Lambert's law, Frank-Condon principle. Now in Jablonski diagram, with the help of diagram, we can explain the fate of excited molecule or how the molecule can undergo relaxation. So here the fate of excited molecule is described with the help of this diagram, fate of excited molecule. So if molecule absorbs the energy, then it will undergo excitation. After absorbing this light, the molecule undergo excitation from bonding molecular orbital to the anti-bonding molecular orbital. And suppose various molecular orbitals, molecule is having various molecular orbitals, and suppose it is sigma, then pi star, non-bonding molecular orbital, then pi star, and then sigma star having the highest energy of this molecular orbital. So in photochemistry, we are mainly concerned with two type of electronic transition. One is pi to pi star, these are this, and another is the n to pi star. So we are mainly concerned with two type of electronic transition in photochemistry. So pi to pi star and n to pi star. So as you can see, n to pi star, it requires less energy and it means higher wavelength, whereas pi to pi star, it requires more energy, that is less wavelength. So usually in photochemistry, we are going to discuss two type of organic molecules, that is olefins, photochemistry of olefins, and photochemistry of carbonyl compound, and photochemistry of aromatic compounds. So there in such compounds we have two type of electronic transitions, mainly two type of electronic transitions we are going to discuss, and these are the two main important electronic transition. One is pi to pi star transition, because it is having both these type of compound is having the double bond, and in carbonyl compounds with this pi to pi star transition you will also have the n to pi star transition. So that is C double bond and C double bond, either any this heteroatom may be there. So such type of electronic transitions we are concerned in photochemistry. Now after absorbing the energy, suppose any molecule absorbs the energy, then first of all it would be in ground state. Suppose this is S0 is in ground state, and after absorbing this energy, that is light energy, then it will undergo excitation, and from this ground state the electron will go into the excited state. So this is, suppose this is S1, it is going into the first excited state S1, and two electrons are initially present in the ground state. And now after getting this energy, light energy, it will go into the excited state, and here these are opposite spin. Here also it is having, after going into the excited state, the spins are opposite. Now there is another possibility that molecule may undergo here the electron, the spin, it may undergo this inversion of this spin may take place. So suppose if one of the spin is like this, and inversion will take place, and another spin is also in a same manner. So these are the two ways that, and finally again the relaxation of this excited electron will again undergo relaxation. So here if you will see here, then the total spin multiplicity, for this total spin multiplicity. So we know that this is equal to 2s plus 1, and where this s is the total spin, S is the total spin. So for in S0 state, because two electrons are in opposite spin, that is S1, so this to S, capital S, this is equal to S1 plus S2, and two are in opposite direction, that is half minus half, and this comes out to be 0. So therefore, in ground state, this 2s plus 1, that is total spin multiplicity, this comes out to be 2 multiplied by 0 plus 1, and this comes out to be 1. So this is in ground state. So in ground state we have the total spin multiplicity in ground state is 1. Now what about this in excited state? That is, this is singlet excited state. Okay, this is a singlet excited state. And now if we calculate the total spin multiplicity over here, then this is 2, and in this case this capital S, this is equal to again S1 plus S2, and both are in same direction spins, so half plus half, and this comes out to be 1. So total spin multiplicity, this is equal to 2 multiplied by 1 plus this comes out to be, because this is in opposite spin, again this half plus half, but two spins are in opposite direction, sorry, so this is half minus half, and it comes out to be 0, and again this 2 multiplied by 0 plus 1, it comes out to be 1. So here also in ground state total spin multiplicity is 1, and in excited singlet state, so this is in ground state, this spin multiplicity is in ground state, this spin multiplicity in excited singlet state, and here the electron, finally the electron spin undergo flipping, and now if it's flipped, then total spin, this is equal to S1 plus S2 again, and this comes out to be half plus half, that is equal to 1, and here the total spin multiplicity is equal to 2 multiplied 1 plus 1, and it comes out to be 3. Okay, so this is electron in ground state. Electrons, when they are present in excited singlet state, total spin multiplicity is 1. When electron is now coming into the the flipping of electrons that takes place, then in that case total spin multiplicity comes out to be 3, and molecule is said to be present in excited triplet state. Okay, so it may be called as this S1, it may be called as this T1, this state is called as the S1, this state is called as the T1. Now this S1 state, so here this is our T1 state, this is our S1 state, and this is our S0 state. So T1 state is the triplet state, and the lifetime of electron in triplet state is very high. So this is the very important triplet state, where in photochemistry this is one of very important state, and here the lifetime of electron is so much high, and it is around 10 to the power minus 3 to 10 to the power minus 5 second is the lifetime in the triplet state. Whereas in excited singlet state, the lifetime is less in comparison to here, in it is around 10 to the power minus 9 seconds. So as the lifetime of molecules in triplet state is long, so that's why it is one of the important state in photochemistry, and most of the photochemical reaction occur via this triplet state. Okay. Now we can if you see what are the main if we talk about the selection rule, what are the selection rule for the electronic transition. So two selection rule here I am going to discuss. Selection rule for electronic transition. So one of the selection rule that is one is the spin selection rule, and this in the spin selection rule it tells delta S, that is total spin, change in total spin multiplicity should be equal to 0. So delta S is the change in total spin multiplicity, and we have found already the total spin multiplicity in singlet ground state is 1. Total spin multiplicity in singlet excited state is again 1. Total spin multiplicity in triplet state, excited triplet state, is 3. So according to this rule, the change in during electronic transition, so during electronic transition delta S should be equal to 0, means change in spin multiplicity during electronic transition, that should be 0. Means the electron can undergo this relaxation or this excitation is very easily when the spin multiplicity is same. So electronic transition is possible when the spin multiplicity remains the same. It should not change. So what type of electronic transition is possible? It means from S1 to this means same in a state of same multiplicity, that is S2 to S1 electronic transition is possible, or from S3 to S2 or S2 to S1. Here the spin multiplicity remains same. Here spin multiplicity is 1, here also spin multiplicity is 1, here also spin multiplicity is 1, and here also spin multiplicity is 1. So electronic transitions are possible between the same spin multiplicity because they are said to be the spin allowed transition. So they are all such type of transition, they are spin allowed transition. Spin allowed transition. So, but it doesn't mean that electron may not undergo transition from the state of different multiplicity. So here means from S1 to T1 also the transition can occur. But this transition, this is spin forbidden transition. Such type of transition is called as the spin forbidden transition. And okay, so this is the spin forbidden transition, and it doesn't mean that it is not the important one. So such transitions are the important transitions also. Such spin forbidden transitions are also very important for forbidden transition. Okay, next that is the selection rule. So first selection rule, when the spin multiplicity transitions are only possible when the spin multiplicity does not change. And another one is the symmetry selection rule. First is the spin selection rule, another is the symmetry selection rule. So according to this symmetry selection rule, during electronic transition is possible when between the orbitals of this suppose the symmetry should not change during the electronic transition. So if you have suppose the symmetry means from S to P here, if transition is taking place from S to P or from P to D, here the symmetry of the orbital changes. It is also called as the orbital selection rule. So the symmetry changes. That's why this is said to be the symmetry forbidden. This is symmetry forbidden transition. Okay, whereas if S to S from same orbital symmetry, S to S, P to P, they are the P to P, D to D, okay, S to S. So such type of transitions, they are symmetry allowed transition. Symmetry allowed transitions. Or suppose I have told you the two main transitions are there in photochemistry we are going to discuss. Now out of these two transitions, pi to pi star transition, this pi to pi star transition, this is symmetry allowed transition. Symmetry allowed transition. whereas this n to pi star transition having different orbital symmetry. So this is symmetry forbidden transition. So but it doesn't mean that this n to pi star transition is not the important one. So n to pi star transition or this pi to, both are very important transition in the organic photochemistry. Okay. Now after that I should explain the Jablonski diagram. Now let me first draw this Jablonski diagram. Suppose if any molecule is in ground state and I represent this ground state by S0, and after absorbing this energy, light energy, molecule may undergo electronic transition, and suppose this is the excited state and this is second excited singlet state. Okay, this is ground singlet state. After getting the light energy, the molecule will go into the electron will go into the excited singlet state, and then it may come to the first excited singlet state, that is suppose this is represented by S1 or this is S1, and then it may come to the next, that is triplet state, represented by T1. Now corresponding to this ground, this is electronic state, this is ground electronic state, this is excited electronic states. So corresponding to this ground electronic state, we may have different many in vibrational states or as well as the rotational state. So here I am only representing the vibrational state. So corresponding to this ground singlet state, the molecule will have different vibrational states, ground vibrational states. So this is suppose V0, V1, V2, V3, like this. These are the ground vibrational state. In the same way, corresponding to these excited states, excited electronic state, okay, we may have different excited vibrational states. These are the different excited vibrational states, and also here also we have different excited vibrational states. Corresponding to this one, we may have different excited vibrational states. Okay. Now here also we may have triplet state. Excited vibrational states. In this triplet state, we have the excited vibrational states also. Now, after absorbing the energy, suppose molecules absorbs energy and it is absorbing so much of high energy that it go to the second excited singlet state. So it will go into the, like this, it can go into the excited Now, after going to this excited singlet state, second excited singlet state, now molecule will undergo relaxation. So various ways, various physical, photophysical processes are there that molecule may undergo relaxation. So one of the, we may describe this into two ways. One is called as the non-radiative relaxation process. Yes, non-radiative relaxation process means the relaxation or emission of light without emitting the light. Okay, so here means during relaxation the light is not emitted, only heat will emitted during the relaxation. So heat emits out here. Here light will not emit out, heat emits out during relaxation, and it is called as the non-radiative relaxation. So this non-radiative relaxation, one of the non-radiative relaxation is the vibrational relaxation. Vibrational relaxation, and this vibrational relaxation is also called as the vibrational cascade. So as you can see here, after getting excited, now the molecule will undergo relaxation. So electron will undergo relaxation, and electron will not directly come into this lower state. Electron will not directly come to its triplet state. So first of all, electron will undergo relaxation. It will come to this state from higher vibrational excited state. So this is higher vibrational excited state. Now it will come down to its next lower vibrational excited state, next lower, and like this it comes to its lower vibrational excited state. So these are called as the vibrational relaxation. This relaxation is called as the vibrational relaxation. Okay, this is called as the vibrational relaxation or vibrational cascade. And here the lifetime of this relaxation is very less. Very easily it may undergo relaxation. So one of the things, this is spin allowed process, spin allowed, and it takes very less time to undergo relaxation, and the lifetime here is only 10 to the power minus 12 seconds is the lifetime. Okay, so after relaxing to here in a ground excited singlet state, okay, now so molecule will come to its end. So suppose here, as you can see, the energy matches to this next excited singlet state, lower excited singlet state. This is S1. So here the energy matches to this lower excited singlet state. So that's why the molecule or electron can come to its cross from this state to the another state, and it will go here, and it will again undergo relaxation to the lower excited vibrational state. So these all process, this is called as the vibrational relaxation. Now when molecule cross from second excited singlet state to the next excited singlet state, and this process is called as the internal conversion, or this is represented by, this is called as the IC, that is called the internal conversion, and this is also non-radiative process. So I may write the second one here is the internal conversion. And this internal conversion, this is suppose from here, you can see from S2 to S1, it is the electron relaxes from S2 to S1. Similarly, molecule or electron may go to the next excited singlet state also. For example, if it goes to the third one, then the relaxation, during relaxation, first of all it will come to the S2, and from this S2 is S1, and then so this internal conversion, it is also, you can see, it takes place between the state of same multiplicity. This S3, S2, S1, they are having the same multiplicity, and total spin multiplicity, as I found, that is equal to 1. So this is also a spin allowed. This is also spin allowed transition, and here the lifetime here is 10 to the power minus 9 seconds. Okay, now as you may see. Now, from after coming to this S1 state, then here the energy of this S1 state matches to the energy of this T1 state here, one of the this excited vibrational state of this, and this ground excited singlet, first ground excited singlet state, energy matches over here, and the molecule or electron may cross from this state to this state, and it is called as the ISC. This process is called as the ISC, or inter-system crossing. Okay, so electron cross from between two different states, that is inter-system crossing, and after coming here, now the electron undergo relaxation and it's come to its ground excited triplet state like this. Okay, so this process, this is also a non-radiative process, and it is inter-system crossing, called as inter-system crossing, or we may represent it by ISC. Here we represent it by IC, that is internal conversion. So electron is coming from excited this singlet state, or from first excited singlet state to the first excited triplet state like this, or otherwise it is also possible that from second to the second triplet state. So this process here, S1 and T1 is having the total spin multiplicity, different total spin multiplicity. That's why this one is the spin forbidden process, spin forbidden transition. Okay, and here the lifetime of this T1 spin, T1, is very, very high. It is longer lifetime. So lifetime of T1 state is 10 to the power minus 3 to 10 to the power minus 5 seconds. So what is what we can say, what is the driving force for this intersystem crossing, or otherwise, because they are spin forbidden process, then only, but the electron crosses this barrier. So the driving force for this is that the lifetime of the triplet state is very high, and that is 10 to the power minus 3 to 10 to the power minus 5 seconds. Due to the higher lifetime of this triplet state, most of the photochemical process occurs via this state. Okay, so now there are some molecules where the intersystem crossing is very efficient, where there are some molecules the intersystem crossing is not so much efficient. In carbonyl compound, the intersystem crossing is very efficient. So if we see example about this carbonyl compounds, ISC is very efficient. Means it occurs very rapidly. And why this intersystem crossing is very efficient? Because in carbonyl compound, the energy gap between this S1 and T1 is very less. So this is due to small energy gap between S1 and T1, or you can say small energy gap between S and T. Okay, and this energy gap is around 5 kilocalorie per mole only. So this is the reason that due to small energy gap, in carbonyl compounds intersystem crossing is very efficient. Whereas in olefins, the intersystem crossing is not efficient. ISC is not efficient. Here means in carbonyl compound ISC is, we can say, around 100%, whereas in olefins the ISC is very less. Okay, so and due to what the reason may be, due to large energy gap between S and T state, that is around how much, around we can say 50 kilocalorie per mole. So that's why due to less intersystem crossing, and in olefins the T1 state is not highly populated. So here in carbonyl compound, due to efficient intersystem crossing, the T1 state is highly populated, and all the photochemical reaction can go via triplet state very easily. Whereas in olefins the intersystem crossing is not very efficient. That's why triplet state is not so much populated, and the reaction via triplet state is not so much easy. So that's why in case of olefin we need the energy transfer. So in my next lecture I will discuss the energy transfer process mainly in olefin type of molecule. So how the energy transfer takes place, and usually some donor molecule can give the energy to the olefin so that the triplet state can easily be populated and reaction can take place via the triplet state. So these are three non-radiative relaxation which occurs via the emission of heat. Now another two relaxation process which are radiative transition. Next one is the radiative relaxation. So this radiative relaxation, so light emits during the, here heat emits during the relaxation process, here light is emitted during relaxation. So either one of the ways, when the electron is present in the excited singlet state, then it can relax back from here to the ground singlet state like this, and this process is called as the fluorescence, and finally it will undergo relaxation via vibrational relaxation called vibrational cascade to its lowest energy ground state. Or otherwise, if electron has come to this triplet state, it may undergo relaxation, and that is called as the phosphorescence. So, and finally it will relax to its lowest ground state like this. So two type of radiative relaxation. One is fluorescence, and this fluorescence, as you can see, it is via S1 to S0. Okay. And both is having the same spin multiplicity, which is equal to 1. So such type of relaxation is spin allowed relaxation, and this spin allowed relaxation, as given you this spin allowed relaxation, it takes place normally in the approximately 10 to the power minus 9 seconds. So here the lifetime is 10 to the power minus 9 seconds. Now another one is the fluorescence. Now this is fluorescence. Now phosphorescence, and this is taking place from this T1 state to the S0 state, and we know that this T1 state and S0 state is having the different total spin multiplicity. This is having total spin multiplicity is equal to 1. This is having total spin multiplicity is equal to it is having 3 and this is having 1. So this is spin forbidden process. This is spin forbidden process, and so the lifetime of this T1 state. So as I have told you, the lifetime is around 10 to the power minus 3 to 10 to the power minus 5 seconds. So here the lifetime is 10 to the power minus 3 to 10 to the power minus 5 seconds. So I have discussed the various relaxation process, and out of this all relaxation process, this intersystem crossing is one of the very important one in photochemistry. So most of the photochemical reaction, it occurs via the triplet state, because triplet state is the highly populated state due to its higher lifetime. So it doesn't mean that the photochemical reaction may not take place via the S1 state, but triplet state being the efficient one, the most of the photochemical reaction will take place via this process. Now in my next lecture, I will explain the energy transfer process in this olefins, where the intersystem crossing is not efficient. Thank you.